For centuries, humanity has looked toward the stars with wonder and fascination, pondering the possibility of life beyond Earth. From the first glimpses of the moon through primitive telescopes to the groundbreaking images of distant planets taken by advanced space probes, our curiosity about the cosmos has only deepened. Yet, in all our exploration, the question has persisted. Can we ever leave our home planet and establish a new future among the stars? Chapter 1. Why Terraform Mars? Mars, the fourth planet from the Sun, stands as one of the most promising candidates for human colonization. With its proximity to Earth, potential resources and geological similarities, Mars presents an intriguing possibility for creating a second home for humanity. But why do we look to Mars, and why now? Why terraform a planet that is inhospitable to life as we know it? In this chapter, we will explore these fundamental questions, delving into the necessity of space colonization, the potential benefits, and the urgency that compels us to seek a future beyond Earth. The need for space colonization. In the 21st century, humanity faces a growing set of challenges that could one day threaten our very existence. Climate change, natural disasters, overpopulation, resource depletion, pandemics, and geopolitical instability are just a few of the crises that could bring about the collapse of civilization as we know it. As our population continues to grow and our natural resources become scarcer, the pressures on Earth's ecosystems intensify. For the first time in history, we are reaching the limits of what our planet can provide. While efforts to address these problems on Earth remain crucial, there is a growing realization that the survival of humanity might depend on our ability to expand beyond our planet. The idea of space colonization, once considered a distant dream, is now viewed as a potential safeguard against extinction. By establishing self-sustaining colonies on other planets or moons, we would create a backup for human civilization. In the event of a global catastrophe, our species could survive and rebuild, preserving the knowledge, culture, and technology we've developed over millennia. Additionally, space colonization offers us the opportunity to unlock the vast resources of the solar system, which could fuel future technological advancements and help address some of the challenges we face on Earth. Mining asteroids for precious metals, harnessing the power of the sun through solar energy, and tapping into the immense potential of other planets could allow humanity to thrive in ways that would be impossible if confined to a single planet. Earth's limitations and existential risks. Despite our incredible technological progress, Earth is not an invincible sanctuary. Our planet is vulnerable to a wide range of existential threats, many of which are beyond our control. Natural disasters like supervolcanic eruptions, massive asteroid impacts, or sudden shifts in the planet's climate could have catastrophic consequences. In the future, humanity may also face threats that we cannot yet imagine, such as runaway artificial intelligence, bioengineered pathogens, or even technological warfare. Even more concerning is the slow but steady degradation of Earth's environment. Climate change, driven by human activity, is already altering weather patterns, raising sea levels, and putting immense pressure on ecosystems worldwide. While efforts to mitigate these changes are underway, it is becoming increasingly apparent that our planet's habitability may be compromised over the long term. Rising temperatures, the depletion of natural resources, and environmental destruction may render Earth uninhabitable in the future. Colonizing another planet could serve as a safeguard against these threats, allowing us to create a second home for our species and increase our chances of long-term survival. Moreover, the inevitability of catastrophic events, such as a large asteroid colliding with Earth, has been a topic of scientific study for decades. While the likelihood of such an event happening in the near future is low, it is still a possibility that cannot be ignored. A major impact event could wipe out entire species, including humanity. Establishing colonies on other planets, particularly Mars, would allow us to mitigate the impact of such a disaster by ensuring that human life is not confined to a single planet. Mars as a candidate for human settlement. Given these challenges and risks, why Mars? Mars is often considered the most viable candidate for human colonization in the solar system. Unlike Venus, which has extreme temperatures and crushing atmospheric pressure, or the gas giants like Jupiter and Saturn, which lack solid surfaces, Mars offers a relatively hospitable environment for future colonization. Mars shares many characteristics with Earth, making it an ideal candidate for terraforming. It has a day length very similar to Earth's, 24.6 hours, and its axial tilt is similar to ours, which means that it experiences seasons. While Mars is currently much colder than Earth, with an average surface temperature of around -60 degrees, 80 degrees Celsius, it is still within the realm of possibility for warming the planet to make it more habitable. Additionally, Mars has a wealth of resources that could be leveraged for human settlement. The planet's surface contains large amounts of water in the form of ice, which could be used for drinking water, agriculture, and oxygen production. Mars also has abundant minerals and elements, such as iron, aluminum, and silicon, which are essential for building infrastructure and sustaining a colony. While Mars's atmosphere is thin and composed primarily of carbon dioxide, it offers an opportunity to create a breathable atmosphere through terraforming techniques, which will be explored in the next chapter. The vision for the future. Terraforming Mars represents more than just a scientific endeavor. It embodies the vision of humanity's future in space. If we can successfully create a self-sustaining colony on Mars, it would be a monumental achievement in human history. It would demonstrate our ability to adapt to and thrive in an entirely new environment, overcoming the challenges of interplanetary travel, life support, and resource management. Moreover, the success of a Martian colony could pave the way for future human settlements on other planets and moons throughout the solar system. With advances in space travel, artificial intelligence, and genetic engineering, humanity could one day spread out across the cosmos, creating a vast network of interconnected colonies. This vision of a spacefaring civilization, where humanity is not confined to one planet, is one of the most exciting prospects of the future. The road to Mars is not without its obstacles, however. The technological, financial, and ethical challenges involved in terraforming and colonizing another planet are immense. Yet, the possibility of creating a future where humanity thrives beyond Earth is a powerful motivator. The next steps in this journey, which will be explored in the coming chapters, will require bold innovation, global cooperation, and a deep commitment to exploring the unknown. In the following chapters, we will delve deeper into the scientific aspects of terraforming Mars, the technologies required to sustain human life on the planet, and the ethical questions that arise when considering the colonization of another world. As we look to the future, it becomes clear that the quest for Mars is not just about survival. It's about the expansion of human potential and the drive to explore and conquer the universe. Chapter 2. The Science of Terraforming, Making Mars Habitable. In the search for new homes for humanity beyond Earth, Mars is the most promising candidate. Despite its inhospitable environment, the planet's potential for supporting life, once transformed, is vast. However, before we can establish colonies on Mars, we must first address the colossal challenge of terraforming, transforming the planet's hostile atmosphere, extreme cold, and barren surface into an environment capable of supporting human life. This is no small feat, but understanding the science of terraforming is the first step toward achieving it. In this chapter, we will explore Mars's current environment and how scientists envision making it habitable. We will examine the atmospheric conditions, temperature, and surface features that define Mars today, and delve into the various methods that may be used to terraform the planet. From warming the atmosphere to producing oxygen and thickening the air, the process of transforming Mars into a suitable habitat for humanity is as complex as it is exciting. Let's break it down step by step. Mars's current environment: atmosphere, temperature, and surface conditions. To understand how we can terraform Mars, we first need to look at the planet's current environment. Mars, often referred to as the Red Planet, is starkly different from Earth in almost every way. The atmosphere, temperature, and surface conditions make it uninhabitable to life as we know it. Atmosphere. One of the primary obstacles to making Mars habitable is its thin atmosphere. Mars's atmosphere is about 100 times thinner than Earth's and is composed primarily of carbon dioxide, CO2, with small amounts of nitrogen, argon, and traces of other gases. Unlike Earth, where the atmosphere is composed of nitrogen, 78%, and oxygen, 21%, the lack of breathable oxygen on Mars makes it impossible for humans or most Earth life to survive without life support systems. Additionally, the thin Martian atmosphere provides little protection from harmful solar radiation and cosmic rays. On Earth, our atmosphere and magnetic fields shield us from the sun's harmful radiation, which is essential for life. However, Mars lacks a significant magnetic field, which allows solar winds to strip away the planet's atmosphere over billions of years, contributing to its current inhospitable state. Temperature. Mars has an average surface temperature of about -60 degrees Celsius, -80 degrees Fahrenheit, with temperatures that can dip even lower at the poles, especially during the Martian winter. This is far colder than Earth, where the average temperature is around 15 degrees Celsius, 59 degrees Fahrenheit. Mars's cold temperatures are primarily due to the thin atmosphere, which cannot retain heat effectively. With little insulation, the planet loses much of the heat it absorbs from the sun. At night, the temperatures can plummet to -125 degrees Celsius, -195 degrees Fahrenheit, making it impossible for water to remain in a liquid state on the surface. This extreme cold poses another significant challenge to terraforming. For Mars to become habitable, we would need to raise the average global temperature significantly to allow liquid water to exist on its surface, one of the key ingredients for sustaining life. Surface conditions. Mars's surface is a mixture of rocky terrain, ancient riverbeds, dusty plains, and massive volcanoes. The planet has the largest volcano in the solar system, Olympus Mons, which stands about 22 kilometers, 13.6 miles high, almost 3 times the height of Mount Everest. The surface also features vast plains and canyons, including the enormous Valles Marineris, a canyon system that is over 4,000 kilometers, 2,500 miles long. While Mars has evidence of ancient river channels and lakes, any liquid water on the surface today is mostly frozen, trapped in polar ice caps or subsurface reservoirs. The lack of liquid water and the extreme surface conditions make it clear that Mars is not yet habitable. Therefore, any attempt at terraforming must address both the temperature and the atmosphere to make the environment conducive to life. Methods of terraforming: warming the planet, thickening the atmosphere, and producing oxygen. To transform Mars into a place where humans can survive, we need to tackle 3 main objectives: warming the planet, thickening the atmosphere to create pressure and trap heat, and producing oxygen for breathing. Let's break down the methods that have been proposed to accomplish each of these tasks. Warming the planet. The primary challenge of making Mars habitable is raising its average temperature to a level that allows for liquid water to exist on the surface. Various methods have been proposed for warming the Martian climate, and each comes with its own set of challenges and benefits. 1. Greenhouse gases. One of the most common methods for warming a planet is through the use of greenhouse gases. On Earth, gases like carbon dioxide, methane, and water vapor trap heat in the atmosphere, keeping our planet warm. By releasing greenhouse gases into Mars's atmosphere, we could potentially create a greenhouse effect that raises the planet's temperature. The challenge is that Mars has very little carbon dioxide in its atmosphere compared to Earth, and what little carbon dioxide is present is locked in the planet's soil and polar ice caps. To increase the greenhouse effect, we would need to release large amounts of carbon dioxide into the atmosphere. This could be done by heating the polar ice caps, which contain frozen carbon dioxide, or by deploying machines that would extract carbon dioxide from the Martian soil. Number 2. Mirrors in space. Another proposed method for warming Mars is the deployment of large mirrors in space. These mirrors would be placed in orbit around Mars, reflecting sunlight toward the planet's surface. This extra sunlight would help to heat the surface and initiate the melting of the ice caps, releasing more carbon dioxide into the atmosphere and further enhancing the greenhouse effect. While this method could be effective, it would require large-scale infrastructure in space and the ability to maintain these mirrors over time. 3. Nuclear solutions. A more direct method involves using nuclear explosions to release heat directly onto the surface of Mars. One idea is to detonate thermonuclear bombs over the polar ice caps to vaporize the carbon dioxide and water ice, releasing large amounts of greenhouse gases into the atmosphere. This approach, known as nuclear terraforming, could dramatically accelerate the warming process. However, it also raises significant ethical and environmental concerns, as the long-term consequences of such explosions on Mars's surface are unknown, thickening the atmosphere. Once the temperature is raised, the next step is to thicken the atmosphere to provide adequate pressure and prevent the newly introduced heat from escaping into space. Without sufficient atmospheric pressure, water would not remain in a liquid state on the surface. It would either freeze or evaporate into the thin atmosphere. Increasing atmospheric pressure could be achieved through several means, most of which involve releasing gases into the Martian atmosphere. The process of releasing greenhouse gases like carbon dioxide could thicken the atmosphere and increase its pressure. Additionally, the use of ammonia, which is a potent greenhouse gas, could further accelerate the process. Ammonia can be found in the outer solar system, and transporting it to Mars for release might be feasible with future space missions. Producing oxygen. One of the final steps in terraforming Mars would be to produce oxygen for humans to breathe. In its current state, Mars has no breathable oxygen in its atmosphere. However, scientists have suggested several ways to produce oxygen on Mars. 1. Photosynthesis. One of the most natural methods of producing oxygen is through photosynthesis. By introducing plants or algae to the Martian surface, we could begin the process of converting carbon dioxide into oxygen. However, for this method to work, Mars would need to have liquid water available, and the surface temperature and pressure would need to be high enough to sustain life. This process could take decades or even centuries to produce enough oxygen for human consumption. 2. Oxygen extraction from carbon dioxide. A more immediate solution could be to extract oxygen directly from the abundant carbon dioxide in Mars' atmosphere. Scientists have developed technologies such as the Mars Oxygen in situ Resource Utilization Experiment, MOXIE, which is designed to convert carbon dioxide into oxygen by using electrolysis. MOXIE has already been tested on Mars as part of NASA's Perseverance rover mission, and it could serve as a prototype for large-scale oxygen production in future human settlements. 3. Artificial photosynthesis. Another approach is to develop artificial photosynthesis systems that mimic the natural process of converting carbon dioxide into oxygen. These systems could be used in combination with plants or algae to help boost oxygen production. Artificial photosynthesis could also serve as a key component of closed-loop life support systems, allowing astronauts and future colonists to recycle the air they breathe. Conclusion. Terraforming Mars is no simple task, but the science behind it is both fascinating and achievable, given the advancements in technology and our growing understanding of planetary ecosystems. By using methods such as releasing greenhouse gases, deploying mirrors in space, utilizing nuclear solutions, and producing oxygen through photosynthesis or chemical processes, we can begin the journey of transforming Mars into a livable environment. However, each of these methods comes with challenges, risks, and ethical considerations that will need to be carefully managed as we move forward. As we explore the potential of terraforming Mars, we also embark on a greater mission to ensure the survival and prosperity of humanity in space. The quest to make Mars habitable is not only about saving our species from extinction, but also about realizing the vision of a future where humanity can thrive across the stars. Chapter 3. Technology and Infrastructure. How would we live on Mars? As humanity embarks on the ambitious endeavor of colonizing Mars, the question of how we would live there, not just visit, becomes paramount. Mars, with its hostile environment, extreme temperatures, low gravity, and lack of breathable air, presents challenges that go far beyond anything we've encountered on Earth. To transform Mars into a livable space for humans, we need sophisticated technology, advanced infrastructure, and self-sustaining systems that ensure survival, comfort, and productivity in this alien environment. In this chapter, we will explore the essential technological innovations and infrastructure required for the Mars colonization project. From spacecraft and transportation systems to habitat construction and the development of sustainable sources of water, food, and energy, each component of life on Mars will rely on cutting-edge science and engineering. The key challenge is not just surviving on Mars, but creating a sustainable long-term presence for humans. Spacecraft and transportation systems, spacecraft design and Mars travel. The journey from Earth to Mars is no small feat, and spacecraft technology is critical to ensuring that humans can safely make the trip to and from the Red Planet. As of today, space agencies like NASA and private companies like SpaceX have been working tirelessly on spacecraft capable of interplanetary travel. The primary transportation issue involves both the transportation of humans and the necessary cargo, equipment, resources, and habitats from Earth to Mars and vice versa. Currently, the journey to Mars takes about 6 to 9 months, depending on the relative positions of Earth and Mars in their orbits. This means that any spacecraft must be designed to support long-duration human missions, providing astronauts with food, water, oxygen, and a means of dealing with radiation exposure over long periods. Spacecraft like SpaceX's Starship are designed with interplanetary travel in mind. They are equipped with life support systems, radiation shielding, propulsion systems capable of long-duration flights, and capabilities for landing on Mars. These spacecraft are essential for ferrying supplies, materials, and eventually human settlers to Mars. Starship's proposed reusable launch and landing systems make it one of the most promising candidates for future Mars missions, reducing costs and improving sustainability. Once the spacecraft reaches Mars, it will need to be equipped with landing systems capable of dealing with the Martian atmosphere, which is only about 1% as thick as Earth's. Technologies such as advanced heat shields, parachutes, retro-rockets, and autonomous landing systems will be critical in ensuring safe landings. Surface transportation on Mars. Once on Mars, efficient surface transportation systems will be needed to move settlers, supplies, and equipment across the Martian terrain. Unlike Earth, Mars has a much thinner atmosphere, so traditional vehicles that rely on aerodynamics won't work effectively. This presents a significant challenge for surface vehicles. Rovers will be essential for transportation on Mars. These vehicles will be designed to navigate the rocky, dusty terrain of the Martian surface while providing a stable platform for the transport of humans and cargo. They will likely be electric-powered, equipped with large wheels to handle the uneven surface, and designed to withstand the planet's extreme temperatures. In addition to rovers, there may also be magnetic or electromagnetic transport systems designed to work with Mars's weak magnetic field. Future technologies might include autonomous drones or high-speed trains designed to efficiently connect various locations on the planet, potentially linking settlements with resource extraction zones or scientific outposts. Habitat construction and self-sustaining colonies. Martian habitats. Design and functionality. Once humans arrive on Mars, the first order of business will be establishing habitats that provide safety and comfort. The habitats must protect from radiation, ensure temperature control, supply breathable air, and allow for long-term human habitation. Mars habitats will likely be sealed domes or underground bases designed to keep out the harsh Martian environment. The thin atmosphere offers little protection from harmful radiation, which is a critical issue for human safety. On Earth, our atmosphere and magnetic field shield us from dangerous cosmic rays and solar radiation. On Mars, this protection is largely absent, so habitats must be shielded with thick materials, such as regolith, Martian soil, water ice, or radiation-resistant composites. These materials can be used to build thick walls or barriers around the habitat, providing a protective shield from cosmic rays and solar radiation. There are various designs for Martian habitats, each with its pros and cons. For example, inflatable modules are lightweight, easy to transport, and can be expanded on site, but they might be vulnerable to micrometeorite impacts. 3D printed habitats, using local Martian materials like regolith, might be more resilient, but would require advanced technologies for construction and long-term sustainability. Self-sustaining colonies. A self-sustaining colony on Mars must be capable of surviving without constant resupply from Earth. To achieve this, the colony needs systems that can recycle air, water, and waste, as well as produce food, oxygen, and other necessary resources. Closed-loop life support systems, CLSS. One of the key technologies for a self-sustaining Martian colony will be the development of closed-loop life support systems. These systems recycle air, water, and waste, ensuring that resources are continuously available for the colonists without requiring frequent shipments from Earth. For example, water recycling systems, like those on the International Space Station ISS, will be necessary to reclaim water from human waste, perspiration, and condensation. Food production systems. Growing food on Mars will be crucial. Since Mars lacks any native edible plants, colonists will need to grow their own food within habitats. Hydroponics, growing plants without soil, and aeroponics, growing plants in air mist environments, are promising solutions. These systems can optimize water and nutrients, minimizing resource use while maximizing food output. In addition, genetically engineered crops might be used to withstand the Martian environment and produce larger yields. Water, food, and energy sources. Water extraction and recycling. Water is one of the most vital resources for sustaining life, and Mars's current lack of liquid water presents a significant challenge. However, Mars does have water ice, particularly at the poles and beneath the surface. Future missions will likely use mining equipment to extract this water from the surface or ice deposits and melt it for use. Additionally, technologies will need to be developed for efficient water recycling within the colony. On Earth, water is used in a variety of systems: drinking, growing food, sanitation, and more, and the same will apply to Martian colonies. A closed-loop water system would continually purify and recycle water used for drinking, food production, and other processes. Energy production. The energy requirements for a Mars colony are substantial, and establishing reliable, renewable energy sources will be crucial. Solar energy is one of the most likely solutions for Mars, given its abundance and the planet's proximity to the Sun. However, since Mars receives only about half the amount of sunlight that Earth does, solar panels will need to be much larger and more efficient than current models. Nuclear power could also play a significant role in Mars's energy infrastructure. Nuclear reactors would provide a reliable and continuous energy source, even during the long Martian nights, which last for about 12 hours Earth time. A small modular nuclear reactor could provide the necessary power to support habitats, water extraction, food production, and other colony needs. In the future, fusion power might offer an even more promising and long-term solution. If fusion energy becomes viable, it could provide almost limitless energy for a Mars colony without the environmental risks associated with other forms of power generation. Food production. Mars offers no natural food sources, so food production will be one of the most complex aspects of a Martian colony. Besides hydroponics, which could be used to grow vegetables and grains, Martian colonies could also explore lab-grown meats. These meats would be produced in bioreactors, requiring minimal resources and space, while offering a protein-rich food source. In addition to plant-based food, advanced technologies could enable synthetic food production, creating food from basic chemical compounds like carbon dioxide, water, and nitrogen. This would allow for highly efficient food production systems that require minimal space and resources. Conclusion. The challenges of living on Mars are immense, but with the right technology and infrastructure, they are not insurmountable. From spacecraft capable of safely transporting humans and supplies to the surface of Mars, to habitats that can protect from radiation and extreme temperatures, and self-sustaining systems that can ensure a constant supply of water, food, and energy, humanity's presence on Mars is becoming more plausible every day. However, each step towards colonization raises new challenges and risks, which require continued innovation and cooperation on a global scale. As we develop the technologies needed to live on Mars, we will not only be preparing for life on another planet, but also pushing the boundaries of what is possible on Earth. The dream of thriving across the stars is within our reach, and with the right vision and effort, we may one day call Mars our second home. Chapter 4: The Ethics of Colonization. As humanity continues to push the boundaries of space exploration, the possibility of colonizing Mars becomes increasingly real. However, as we develop the technology and infrastructure necessary to transform Mars into a second home for humanity, we are confronted with a range of ethical questions. These issues not only impact the future of Mars, but also reflect broader moral dilemmas that humanity faces in its quest for expansion beyond Earth. Should we terraform Mars? What rights, if any, do potential Martian ecosystems have? And who gets to decide the future of Mars? These are just a few of the critical ethical questions that will need to be addressed as we begin to shape the future of the Red Planet. Should we terraform Mars? The first ethical question that arises in the context of Mars colonization is whether we should terraform the planet at all. Terraforming is the process of altering a planet's environment to make it more hospitable to human life, and it involves massive changes to a planet's atmosphere, climate, and surface conditions. While this concept may seem like a technological triumph, it raises several ethical considerations. The moral responsibility to preserve Mars. One of the most significant ethical concerns surrounding terraforming is whether humans have the right to radically alter another planet. Mars, like Earth, has its own history, and its current state has been shaped over billions of years by natural processes. Although Mars is not home to any known life forms, its environment may still harbor ecosystems or microbial life that we are unaware of. Is it ethical for humans to change the planet's conditions without fully understanding the potential consequences? Some argue that the preservation of Mars in its natural state could be important for scientific purposes. Mars offers a unique opportunity to study planetary history and the potential for life beyond Earth. By preserving its environment, we allow future generations to explore and learn from the planet's untouched landscape. There is also the argument that tampering with Mars could set a dangerous precedent for the exploitation of other planets. If we terraform Mars, would we then feel justified in altering other planets and moons in the solar system, potentially causing irreversible harm to their environments? The need for humanity's survival. On the other hand, there is a compelling argument that terraforming Mars is a necessary step for the survival of humanity. Earth faces numerous existential threats, from climate change to asteroid impacts to the possibility of global pandemics. Colonizing Mars provides an insurance policy against the potential extinction of humanity. In this context, terraforming Mars could be seen as an ethical imperative, offering a new frontier where humanity can continue to thrive and evolve. Advocates of terraforming argue that making Mars habitable is not only a technical challenge, but a moral one. Humanity, they suggest, has a responsibility to ensure its own survival by seeking out new worlds to colonize. If we have the capability to terraform Mars and create a new home for future generations, is it not our duty to do so? In this sense, terraforming becomes a necessity for the continuation of our species and the preservation of human civilization in the face of the unknown. The debate on human impact. Yet, one of the most challenging aspects of terraforming is the balance between progress and preservation. If we terraform Mars, we will inevitably introduce human activity, infrastructure, and resource extraction, all of which will have a profound impact on the planet. While proponents of terraforming may argue that this process is necessary for humanity's survival, opponents contend that we should focus on preserving the natural state of planets and ecosystems in the universe. The question of whether we should terraform Mars is a complex one, with no easy answer. It is a debate between the preservation of the planet's natural environment and the human drive to expand, survive, and secure a future for humanity. As we move forward in our exploration of space, it will be important to engage in thoughtful, inclusive discussions about our ethical obligations toward other planets. Rights of potential Martian ecosystems. Another ethical consideration in the colonization of Mars is the potential existence of Martian ecosystems, even if they are microbial in nature. While Mars has long been considered a barren, lifeless planet, recent missions have uncovered evidence that liquid water once flowed on its surface, and there are signs that the planet may have been capable of supporting microbial life in the past. Furthermore, there is still the possibility that life, albeit microbial, exists on Mars today, hidden beneath its surface or in the subsurface ice. The potential for life on Mars. If life does exist or has existed on Mars, it raises a critical question about the rights of Martian ecosystems. Even microbial life forms deserve ethical consideration. Just as Earth's ecosystems are protected by laws and conventions to prevent harmful practices such as pollution and habitat destruction, should Mars be similarly safeguarded? Should we recognize the rights of Martian life forms to exist and thrive, even if they are microscopic and vastly different from Earth-based life? Some believe that the ethical principle of biocentrism, which holds that all forms of life have inherent value and the right to exist, applies to Mars as well. Under this viewpoint, the discovery of life on Mars would make the planet a special case, warranting the protection of its ecosystems and habitats. This perspective argues that the potential for life on Mars should guide our actions and prevent us from taking any steps that might harm or destroy Martian ecosystems before we fully understand them. The impact of human activities. Human activity on Mars, including terraforming, resource extraction and colonization, could potentially disrupt any native Martian life forms, especially if these life forms are microorganisms. Even the introduction of Earth-based life forms, such as plants, bacteria or animals, could pose a threat to native Martian life due to the risk of contamination. The ethical dilemma arises when we consider whether human colonization of Mars could lead to the extinction of native life, or even whether we should attempt to avoid any interaction with Martian ecosystems altogether. At the same time, it is important to consider the role of humanity in the universe. Some argue that life on Earth is not the only form of life that matters, and that we should aim to expand the diversity of life throughout the universe. In this view, introducing Earth-based life to Mars could be seen as part of a broader ethical imperative to cultivate life across the cosmos. However, this perspective is fraught with moral risks, as it could lead to the unintended destruction of Martian life forms before we even understand their full potential. Chapter 5. Challenges and Risks. Colonizing Mars, a venture that represents humanity's boldest leap into the cosmos, is fraught with numerous challenges and risks. While the prospect of establishing a human presence on another planet is awe-inspiring, the reality of living on Mars involves overcoming significant scientific, technological, environmental, and human factors. This chapter delves into the primary challenges and risks associated with Mars colonization, focusing on radiation exposure, the psychological effects on settlers, and the economic and political barriers that could impede progress. Radiation exposure and human health concerns. One of the most significant dangers to human life on Mars is exposure to cosmic radiation and solar radiation. Mars lacks a magnetic field and a thick atmosphere like Earth's, both of which protect us from harmful space radiation. As a result, the Martian surface is bombarded with high-energy particles from the Sun and deep space, which could pose serious health risks to humans over long durations of exposure. This issue is further complicated by the fact that human colonists on Mars will spend months or even years outside of Earth's protective shield. Cosmic radiation and solar storms. Radiation is classified into two primary types: cosmic rays and solar particles. Cosmic rays are high-energy particles that originate from outside our solar system, traveling at nearly the speed of light. These particles can penetrate deep into the human body, damaging cells and DNA, which could lead to cancer, organ failure, and other long-term health problems. In addition, solar storms, which are intense bursts of radiation from the sun, can be even more dangerous, especially during periods of heightened solar activity. If a solar storm occurs while settlers are on the Martian surface, it could expose them to lethal doses of radiation in a short amount of time. Given these threats, one of the most critical challenges of Mars colonization is developing effective shielding to protect astronauts from radiation. Potential solutions include constructing habitats below the Martian surface, where the planet's regolith, soil, could provide some natural protection, or building radiation-resistant structures using advanced materials like hydrogen-rich compounds. Another idea is the use of electromagnetic shields that could mimic Earth's protective magnetic field. Nonetheless, long-term exposure to radiation remains a major concern, requiring further research into protective technologies and countermeasures. Biological effects. Radiation not only poses a cancer risk, but also affects human physiology in other ways. Prolonged exposure to space radiation can cause damage to the immune system, impair cognitive function, and lead to cardiovascular diseases. Furthermore, Mars's lower gravity, approximately 38% of Earth's gravity, could cause muscle atrophy and bone loss, particularly during extended stays. The combination of radiation exposure, weakened bones, and atrophied muscles presents a severe challenge to the health of Mars colonists, making it essential to find ways to mitigate these risks before long-term missions can be undertaken. Psychological effects of living on Mars. In addition to the physical challenges posed by radiation and the Martian environment, there are profound psychological risks associated with living on Mars. A mission to Mars could involve months of travel to and from the planet, followed by years of living in an isolated, confined environment. These conditions could lead to a range of psychological and emotional challenges, affecting both the individual and the collective well-being of a Martian colony. Isolation and loneliness. One of the most immediate psychological risks for Mars settlers is the feeling of isolation and loneliness. The vast distance between Earth and Mars means that communication will be delayed by up to 20 minutes one way, preventing real-time conversations with loved ones and friends. Settlers will be isolated from the world they know, and the lack of social contact could result in feelings of depression, anxiety, and helplessness. Prolonged isolation is known to have significant psychological effects, including sleep disturbances, mood swings, and cognitive fatigue. The mental health of colonists will require careful monitoring, as well as strategies for maintaining social cohesion within the crew. The sense of being cut off from Earth will likely be exacerbated by the harsh and inhospitable environment of Mars. The barren, desolate landscape, with its dust storms, extreme temperatures, and lack of biodiversity, could contribute to feelings of hopelessness and despair. Maintaining morale among settlers will be a significant challenge, requiring the creation of psychologically supportive environments and coping strategies. Group dynamics and conflict. Living in close quarters with a small group of people for extended periods, as would be the case in a Martian colony, could lead to interpersonal conflicts. Without the option for physical space or the ability to leave the colony, tensions could rise among the settlers, particularly under the stress of difficult living conditions. Crew members will need to be carefully selected, with an emphasis on psychological resilience, conflict resolution skills, and the ability to work as part of a team. Failure to address the psychological well-being of colonists could lead to serious problems, including stress-induced breakdowns, interpersonal violence, and the inability to function as a cohesive group. Coping mechanisms and mental health support. To counteract these challenges, future missions to Mars will need to implement robust psychological support systems. This might include regular communication with Earth, access to virtual reality or other immersive entertainment, and therapeutic practices like mindfulness and meditation. There could also be dedicated professionals on the crew, such as psychologists or psychiatrists, who would be trained to manage mental health challenges in space. Furthermore, the design of habitats and social systems should take into account the psychological needs of settlers, ensuring that they have access to privacy, recreational activities, and emotional support to maintain mental well-being. Economic barriers. While the technological and human challenges of Mars colonization are significant, there are also profound economic and political obstacles that must be addressed. Colonizing Mars is an immensely costly endeavor, requiring the development of new technologies, the construction of infrastructure, and the provision of essential resources. Cost of Mars colonization. Estimates suggest that a manned mission to Mars could cost anywhere from $100 billion to over $1 trillion, depending on the scale of the mission and the technologies developed. This enormous financial burden presents a major hurdle for governments and private entities. The costs of transportation, habitat construction, life support systems, and ongoing maintenance would require substantial funding, likely necessitating international cooperation and long-term investment. One of the primary concerns is how to sustain the colony economically once it is established. Mars is resource poor, and transporting supplies from Earth would be both expensive and logistically challenging. To be self-sustaining, Martian colonies would need to develop local resource utilization strategies, such as mining for water ice, producing oxygen and fuel, and growing food. However, even with these systems in place, the financial costs of establishing and maintaining a colony would be astronomical, and it is unclear how such a venture could generate the economic return necessary to justify the investment. Conclusion. The challenges and risks associated with colonizing Mars are vast and varied. From the dangers of radiation exposure and the psychological toll of living in isolation, to the economic and political barriers that must be overcome, the journey to Mars will be fraught with difficulties. Nevertheless, these obstacles are not insurmountable. With continued research, innovation, and international collaboration, humanity can address these challenges and pave the way for a future where life on Mars is a reality. However, careful consideration of the risks, combined with a robust plan for overcoming them, will be essential if we are to ensure the success and sustainability of Martian colonization. Chapter 6: Beyond Mars, the Future of Humanity in Space. Mars represents only the beginning of humanity's journey into the cosmos. While its colonization is an ambitious goal, the long-term survival of our species may require us to expand beyond a single planet. In this chapter, we explore the next steps in human space expansion, examining other planets and moons as potential homes, the possibilities of interstellar travel, and the ultimate vision of becoming a true spacefaring civilization. Other planets and moons as potential homes. While Mars is often considered the best candidate for human colonization, it is not the only celestial body that could support human life in some capacity. Other planets and moons within our solar system present unique opportunities and challenges, each requiring its own set of technological advancements to sustain human habitation. Venus, a floating colony in the clouds. At first glance, Venus appears to be one of the least hospitable places for human settlement. Its surface is a hellish landscape, with temperatures exceeding 460 degrees Celsius, 806 degrees Fahrenheit, crushing atmospheric pressure and clouds of sulfuric acid. However, the concept of a floating city in the Venusian atmosphere has gained attention among scientists. At an altitude of approximately 50 kilometers, Venus's thick atmosphere provides a region where temperatures and pressures are surprisingly Earth-like. A colony of floating aerostats, large balloon-supported habitats, could hover within this region, allowing humans to live and work in a more temperate environment. While challenges such as the high levels of carbon dioxide and the corrosive nature of Venus's clouds must be addressed, Venus offers a potential alternative to Mars for human expansion. The moons of Jupiter and Saturn, ice worlds with hidden potential. Some of the most intriguing destinations for future human colonies lie among the icy moons of the outer planets. Jupiter's moon Europa and Saturn's moon Enceladus, for instance, are believed to harbor vast subsurface oceans beneath their thick ice crusts. These environments could potentially support microbial life, making them critical locations for astrobiological exploration. Titan, Saturn's largest moon, is another compelling candidate. Unlike any other moon in the solar system, Titan has a thick atmosphere, primarily composed of nitrogen and stable liquid bodies on its surface, although they consist of liquid methane and ethane instead of water. Titan's atmosphere provides some protection from cosmic radiation, and its low gravity would allow for easier transportation of materials and movement of colonists. With the right technology, Titan could become a key location for human expansion beyond Mars. The asteroid belt, mining and deep space habitats. Between Mars and Jupiter lies the asteroid belt, home to countless rocky bodies rich in metals and other valuable resources. Establishing space habitats within the asteroid belt could serve multiple purposes: resource extraction, scientific research, and as a stepping stone for further space exploration. These habitats could be constructed from hollowed-out asteroids or built from materials harvested from the belt itself. Interstellar travel and the search for habitable exoplanets. While our solar system offers various possibilities for expansion, the ultimate goal of space exploration is to venture beyond it. Humanity has long dreamed of reaching other star systems and finding new Earth-like worlds to call home. However, the vast distances between stars make interstellar travel one of the greatest challenges of all. The nearest exoplanets, potential new Earths. Astronomers have identified thousands of exoplanets, planets orbiting other stars, many of which exist in their star's habitable zone, where conditions might allow liquid water to exist. Some of the most promising candidates include Proxima Centauri b, orbiting the closest star to the Sun. Proxima Centauri b lies within the habitable zone, though it is subject to intense stellar radiation. TRAPPIST-1 system. This system contains multiple Earth-sized planets, some of which may have conditions suitable for life. Kepler 452b, often referred to as Earth's cousin, this exoplanet orbits a Sun-like star and could have a climate similar to Earth's. While finding these planets is an important step, actually reaching them is an entirely different challenge. Propulsion technologies for interstellar travel. Interstellar travel requires speeds far beyond what traditional chemical rockets can provide, necessitating the development of advanced propulsion systems capable of sustaining acceleration over vast distances. Scientists are currently exploring several promising concepts that could one day make interstellar journeys feasible. Nuclear fusion propulsion. This method would utilize controlled fusion reactions, similar to those that power the Sun, to generate immense thrust with high efficiency. Unlike chemical rockets, which burn fuel quickly, fusion propulsion could sustain acceleration over extended periods, significantly reducing travel time to nearby star systems. While practical fusion propulsion remains a challenge, advancements in fusion energy research are bringing this technology closer to reality. Light sails. These spacecraft would be propelled by the pressure of photons from powerful laser beams or sunlight. Over time, light sails could accelerate to speeds nearing 20% of the speed of light, making them a viable option for interstellar probes. Projects like Breakthrough Starshot propose using laser arrays on Earth to propel small, lightweight probes to Alpha Centauri within a few decades. The main challenges involve developing highly reflective, ultra-thin sail materials and precise laser targeting over vast distances. Antimatter propulsion. When antimatter and matter collide, they annihilate each other, releasing enormous amounts of energy. This reaction could, in theory, generate thrust far more efficiently than any known propulsion method, potentially allowing spacecraft to reach speeds close to the speed of light. However, producing and storing antimatter remains an enormous challenge, as even a tiny amount requires vast amounts of energy to create in particle accelerators. Warp drives. Theoretical models, such as the Alcubierre warp drive, suggest that instead of moving through space, a spacecraft could manipulate space-time itself, contracting space in front of it and expanding it behind, to effectively surf across the cosmos at faster-than-light speeds. While still speculative, some physicists are investigating whether exotic matter or negative energy could make such a drive possible. If ever realized, warp technology would revolutionize space travel by allowing humanity to reach distant stars almost instantaneously. While each of these propulsion technologies presents significant scientific and engineering challenges, they represent potential pathways for humanity to venture beyond the solar system. As research progresses, a combination of these technologies, or breakthroughs in entirely new concepts, may one day make interstellar travel a reality.